Hi everybody, my name's Nick and welcome back to Lafayette Systems. I'm building an amateur rocket with custom 3D printed airbrakes and a custom flight computer so it can fly to a precise apogee altitude. Today we're going to talk about simulations. I'm going to show you how to simulate a rocket flight in MATLAB and SIMULINK. I'm going to show you how you can control the altitude of a rocket with airbrakes, and then we're going to compare 3 different guidance and control laws to see which one performs best in the simulation. I'm actually building a second amateur rocket with a guidance and control system right now. This rocket is called Sapphire. It is a supersonic guided amateur rocket. It's got a custom flight computer in its nose, its data link antennas are printed onto its strakes, and I have a custom 3D printed control actuation system that steers these fins in the rear. I'm going to be releasing a video very soon on how I designed and 3D printed this custom control actuation system for Sapphire. Now before we fly Sapphire, we're going to have to do a lot of simulations. We need to make sure that the vehicle is statically stable, and we also need to do the preliminary gain tuning that'll make sure the vehicle is safe on its first flight. About a year ago, I did a video on the simulation tools that I use for this rocket called Diamond X. Much like Sapphire, it uses these tail control surfaces to steer, and I flew this rocket to GPS waypoints at about 1 kilometer in the air. In that video, I talked about all the simulation tools that I use to design, tune, and test amateur rockets. But unfortunately, I couldn't go into a lot of detail on how I did some of the MATLAB and SIMULINK portions to do guidance and control tuning. If you squint and look really closely, you'll notice that this rocket kind of resembles... American export control restrictions limit what I can talk about for rockets that actively steer themselves. The cool thing is with this Airbrakes rocket that all it can change is its final apogee altitude. It can't steer left or right. This makes our simulation a lot easier, and it also means that there are a lot fewer restrictions placed on me talking about them. So today we're going to do just that. We're going to talk about rocket simulations in the context of our Airbrakes rocket. By the end of today, we're going to be simulating our own Airbrakes rocket flights and doing the guidance and control tuning for a couple of different control systems. So first, why should we do simulations? Launching rockets is tons of fun. It can also be pretty expensive and pretty dangerous if something goes wrong. As we add active control systems to our rockets, all 3 of those factors go up. With a rocket like Sapphire, crashing it can mean thousands of dollars down the drain, and it can make it very unsafe for people on the ground. We want to be really confident that a rocket's going to work, or at least behave safely, before we ever head out to the launch site. Modeling and simulation encompasses a variety of techniques that help us do that. With a good model, your rockets will work better, be more predictable, be safer, and it'll save you money. The second reason to use modeling and simulation is something called sensitivity analysis. Sensitivity analysis basically answers the question, if you change some little part of your rocket, how much does it change the overall behavior of the flight? If you make your fins 1 millimeter shorter, what happens to the rocket? For some rockets, it does basically nothing. For other rockets, it'll make them unstable. For guidance and control systems, that's very important. Things like, if I have a tiny bit of backlash on my control surfaces, how much does that affect my rocket flight? Sensitivity analysis is something that we'll explore today, and it's a very important part of your rocket designs, especially as you start making them more complex. If you're going to be doing simulations like this, having a little bit of background in math and physics can be really helpful. I know some of you haven't gotten to those classes yet, and some of you either took them long ago or never had the opportunity or inclination. The good news is that if you have a computer or a phone, and I know you do because you're watching this, you can start learning math and science today with this video's sponsor, Brilliant.org. Brilliant has thousands of online lessons covering math, science, programming, AI, and more. Warning, we are going to be doing some algebra in about 5 minutes, and if the thought of moving terms around in an equation makes you want to pass out, the Solving Equations course on Brilliant is perfect for you. As an engineer, I use calculus every single day, whether it's deriving equations of motion or designing new simulation behavior. Does the integral symbol give you flashbacks to failing a freshman year calc exam? Me too. I don't know if Brilliant.org can fix that, but it can help you finally understand calculus, which is even better. If you're ready to start learning today for free, go to Brilliant.org/Lafayette, scan the QR code on screen, or click my link in the video description. Brilliant's also offering simulation experts just like you 20% off an annual premium subscription. That gives you unlimited daily access to all of the courses that Brilliant has to offer. So we're here in MATLAB. MATLAB is an IDE, an integrated development environment, and its own language. So when we code in the MATLAB IDE, we're coding in the MATLAB language. Right here we have the command window. So we can just do math in here. We can do like 4 plus 5, and we can see we get the answer out. MATLAB's very good at matrix math. That's what the MAT in MATLAB stands for. And we will be using a little bit of the command window to load some of our data in when we do some of our guidance and control laws. But first, let's get our simulation set up. One of the add-ins to MATLAB is SIMULINK, and you can see we have the SIMULINK button right here. SIMULINK is a drag and drop block type of programming. If you've ever done Scratch as like an intro to programming, it's very similar to that, except you can do extremely sophisticated stuff with it. So here in SIMULINK, we can create a new blank model. Let's create a new model. SIMULINK is based around these blocks that we can add by just double-clicking. So to start with SIMULINK, we just need to add a block. We can double-click and we can search something up. We're going to start with the 3 degree of freedom or 3DOF body axis block. 3DOF. There it is. So this block is in the aerospace block set, and it only has 3 degrees of freedom. So there's kind of vertical motion, horizontal motion on one axis, and then rotation. There's also a 6DOF block, and I use that for my more complicated guidance and control simulations, but we're not going to be doing any of that today. We're just going to do this simple 3DOF block. This takes in force in the x-axis, force in the z-axis, and then moment around our one rotational axes as inputs. And those are in the body axes. And then it outputs all sorts of stuff. You can see angles, angular rates, we can see position, velocity, and acceleration. The other block we're going to use a lot is called the scope. This lets us output data. So if we take our scope here, let's output this on position. In terms of force, we don't have any forces in, but this block does have gravity internally. So we're just going to leave the gravity there. Let's run this and we'll see what our scope outputs. And here's our output. So you can see on our x-axis, we're linearly increasing. We have a constant velocity on x, and then our y-axis is increasing because this is us falling under gravity. So we can see we have some initial x velocity. If I go into this, we will see that our initial velocity is 100. Let's set that to 0 and we'll run it again. We'll see a little bit different behavior. You can see now our x-axis doesn't have any motion. We've just removed all of our velocity, but our z-axis is still showing this motion of us falling under gravity. You'll notice that the gravity is kind of seemingly pointed up in this case. In this coordinate system, the z-axis is kind of pointed down. So when we're falling downwards in the positive z direction. If we want to change that, if we want a more traditional z being up approach, I can set gravity to negative. So I'll do that here, and we'll see that in the z-axis, we will behave the opposite way. We'll now go in the negative z direction, which is kind of like us falling from a standstill. And there we go. We see our z-axis position is increasing exponentially. If I do another scope, let's do a scope on our velocity. What we expect to see is that our x-axis velocity doesn't change, but our z-axis velocity increases linearly with gravity. We'll get another scope, and it's always good to name these, so do position, and we'll do velocity. Let's connect our velocity scope up to velocity. Just kidding, that's acceleration. We'll do velocity, and we'll run this. And you can see our z-axis velocity is decreasing linearly as we accrue velocity in the negative z direction. So this is the behavior of our rocket starting at position 0 and then falling under gravity. We're not modeling that the ground exists, so it just kind of like it falls through the earth. What we do want is a little bit of initial force, some force to push the rocket up in the air. So let's add that. One way to do this is with something called a step function. A step function is a function that has 2 possible output values, and then it changes between those 2 values one time at a given time. So if I pull up a step function here, you can see the default is that at step time equals 1 at 1 second, we go from an initial value of 0, whatever units the step function is, to a final value of 1. If we're using like an F44 engine, so we should start with an initial value of about 44 newtons, that's the average force of that engine, and our final value should go to 0 when our engine burns out and there's no force. And for the F44, that occurs at about 1.8 seconds. So we have about 1.8 seconds of burn. We can plug this into our Z force, and then let's run this. We should expect to see the rocket kind of go upwards and follow a parabolic curve down. There we go. So this is our rocket under thrust. We burn out about right here, and then our rocket coasts up to about 250 meters in the air, and then you can see it starts to fall back down. You know that this simulation ends at 10 seconds. If I stretch this out to about 20 seconds, we'll see us actually hit the ground. Yep, and we hit the ground, and this isn't modeling that it stops at the ground, so it just keeps falling straight through the crust of the Earth. So this is actually the right behavior under thrust. We've now modeled the thrust of a rocket engine. There's more complicated models than just a step function. This is assuming that the motor thrust is constant when it's under burn, and then as soon as it stops burning, it goes to 0, which turns out is actually not a terrible way to model it. But this isn't modeling any aerodynamic effects. So let's try to add some aerodynamic effects. That will be a force, and it's a force due to drag. One of the assumptions we're going to make here is that drag only acts in the z direction. Our rocket's only traveling in the z direction. We have no lateral motion. That's going to make all the math a little bit easier for us. To model the drag, we're going to use something called a MATLAB function block. This lets us do a little block of code that takes some inputs, does a bunch of calculations, and then gives us some outputs. Do a MATLAB function here, and we'll just put it down here. So we want to be modeling the drag equation. What is the drag equation? So here is the drag equation. This is solving for CD, our drag coefficient. We actually don't want to solve for a drag coefficient. We need to do a little bit of algebra, rearrange the equation, and solve for the drag force. We're acting with forces right now, and we want to add our drag force to our motor force. So let's type this equation in. We have drag equals 0.5 times CD times, we'll do rho, that is the atmospheric density, times A, that's our reference area, times our velocity squared. We'll do v squared. So now we just need to make sure that all of these variables are defined either in this function as static values, or we pass them into this function as an input. The stuff that doesn't change is like our reference area. Our reference area is just the cross-sectional area of our rocket, and it's just a number we multiply the drag coefficient by, so we can kind of standardize drag coefficients between rockets of different sizes. In this case, our reference area, A, equals 0.00353. That's in square meters, and that's something that you can get from OpenRocket. You just need to make sure that you have the right units there. OpenRocket might be reporting it in a different set of units. Next, we'll do what our rho is. That is the atmospheric density. That's about 1.44 kilograms per cubic meter at sea level. I'm not quite at sea level, but we'll roll with that for now. Equals 1.44. There we go. And then what other inputs do we need? First, we need a drag coefficient. So if we're going to start modeling our rocket without any air brakes, I can pull my drag coefficient from OpenRocket, and I know that that's about 0.4. So we'll do CD equals 0.4. And the last thing we need to pass in is our velocity. This is going to be the velocity in the z direction, but that's going to change over the course of the simulation. So I'll just pass that in as an input. And the output here, we want our drag force. And we'll call this, what should we call this? We'll say it's like compute drag. There we go. And then I'm just going to replace this last set with end. Now we need to make sure that we have the right sign on our units. So in this case, if our velocity is positive, meaning that we're traveling upwards away from the ground, our drag force should be acting in the negative z direction. Well, in this case, if our velocity is positive, the drag force is going to be positive. Our motor force was also positive. So if we left it like this, this would mean that our rocket is accelerating due to drag in the upwards direction, which doesn't really make any sense. So we're going to add a negative sign here to make sure that our drag force is applied in the opposite direction of our vehicle's motion. This model actually just applies it towards the ground no matter how your rocket's traveling, so this will actually accelerate our rocket towards the ground, but if we did a little bit of vector math, we could apply that. In our case, we only care about the drag force on the way up, and then we'll just stop our simulation at apogee, so this is fine for now. So now we have two forces. We have our motor force in the z direction, and we also have our drag force. We need to add these together. We're going to use a sum block. This just lets us add a couple of numbers together. So we'll just do this. We'll rearrange our inputs, and we can see this force in the z direction is now the sum of our motor force and our drag force. We do need to get our velocity, and we only want the velocity in the z direction. If we still get our velocity outputs, we have u and w in meters per second, so that's how we know it's velocity. If we open this velocity thing, we can see that the first one looks like in the z direction, right? Here's our motor accelerating us, and then this is gravity slowing us down, and that's the second one listed. So we only, in this case, we want the w variable. Now, if we want to pull one of the variables out of a vector, this is a vector with two elements, we can use something called a demux block, D-E-M-U-X. So you can see with this setup, we have one input and two outputs. If we do three outputs, this would demux a three-element vector, but we have a two-element vector here. So let's change this back to 2. Let's change that back to 2. There we go. And so if I peel this off, we take the second element, that's our W, our Z velocity, and we'll plug it into our compute drag equation. We're also going to add a scope a couple places. First is drag force. We just want to be able to see the drag force, make sure our model is correct, and we also want scope. Let's do a scope to compute or to read out the total force. Total force. All right, so let's run this, and we should see a little bit different behavior. Our rocket shouldn't go quite as high as it decelerates now due to drag and gravity. So you can see in our total force plot here, we can see two different behaviors. First is our motor thrust. It starts off at 44 newtons, just like we said, and then about 1.8 seconds, it stops. And you can see our total thrust is decreasing because as our rocket accelerates, our drag force is opposing our motor thrust force. As soon as our motor burns out, our force goes negative. Here's 0. Our force goes negative to about -4 newtons of drag force. And as we get to apogee, that drag force goes to 0 because we have 0 velocity. As we then fall, our drag force continues, and again, that's the wrong direction, but we only care about our rocket's behavior up to about apogee at 7.5 seconds. If we look at our position, we should see that we didn't quite go as high. I'm again going to limit our plot here to just our rocket's behavior until it gets to apogee. And we'll expand that out. And we can see instead of at 250 meters like we were last time, we're much lower. We're only at like 215 meters. So that looks like our drag force model is working pretty good. What you will see is that we have kind of discrete steps here. It's a little hard to see, but this simulation is only running a couple of time steps. One thing I can do is I can open my model settings and I can force the simulation to run a fixed time step. So if I choose fixed time step, I'm going to, instead of saying auto, we'll do 0.001. Maybe 0.01. Let's try this. This means that there's 100 simulation steps per second. If I do 0.01, there's 1,000 simulation steps per second. Let's try that, and let's see if our plot changes. This will take a little bit longer to run, but the computer's pretty powerful, so it goes through it pretty fast. And actually, I'm going to change my stop time to about 8 seconds, which is after we reach apogee. It means we don't have to run the simulations for as long. There we go. So if we look at position now, we can see that this curve is a lot curvier. There's a lot more simulation steps we're taking. And we're still going to about 215 meters. One thing that we do want to do is be able to output our apogee altitude. I'm going to do that in a little bit of a funky way. We do want to get our Z position. That's our apogee altitude. So I'm going to do another demux. Demux. It's still 2 elements. And I know from looking at my position, we care about the second element in this vector. So we'll connect this here. And we'll pull this guy out. This is our altitude, our Z position. And then also do a display. Now if I just do this, this display will always show what our current altitude is, which isn't quite what we want. Of course, we want our apogee altitude. And as you can see, 204 meters, that's less than our maximum. One way to just record our apogee altitude, and this is a little funky, this is with something called a rate limit block, rate limiter. A rate limit block just means that the output changes, but it's limited in how much it can change per unit time by a specific value. So let's say we had a rate limit of 10. This would mean that every second, regardless of what the input's doing, this output can only change plus or minus 10 feet, or in this case meters, every second. We can give it different rate limits on the rising and falling slew rate to get some interesting behaviors. So on the rising, we're just going to add a bunch of 9s. This means that the output can change as fast as it wants with the input as long as the input's increasing. The falling slew rate will set to 0. This means that the output of this rate limit block can never go down. So in this case, we've just created basically a maximum function. If the number going in increases, the output of this rate limiter block will increase accordingly. But as soon as the input decreases, the rate limit will hold it at whatever that input was maximum. So as we run this now, we should be showing our maximum altitude, 207 meters. I'm going to change this to apogee altitude. And there we go. So as we change different things, we'll see this apogee altitude change. Let's change our motor. Let's go 2 seconds of motor thrust instead of 1.8. And our apogee altitude should increase. Look at that, 247 meters, pretty good. If we increase our drag coefficient, let's make that 0.5, we should see our apogee altitude now go down. We were adding more drag. The rocket shouldn't quite fly as high. 236, we went down a little bit. So here's our rocket model. We can now model different motors and different amounts of drag. If we weren't doing any active control systems, this would actually be kind of it. We're not modeling any lateral change in position, and we're also not modeling the rocket like pitching or yawing around at all. But if you're just looking to predict a rocket's apogee, if you know the motor thrust and you know its drag coefficient, this will do the exact same thing that OpenRocket does. You can also look at these plots to get what your burnout altitude is, what your apogee altitude is, what your apogee time is, and you can do things like tuning the ejection delay on your rocket motors. So basically this is kind of like crappy OpenRocket. But we can do some interesting stuff in MATLAB that OpenRocket can't do. So let's do a little bit of guidance and control. In our MATLAB function compute drag, I'm going to call this something else, drag calculator. We're only taking in velocity, but we're assuming that our drag coefficient is constant. With our Airbrakes rocket, we're going to be actively changing our drag coefficient. So in here, instead of setting our drag coefficient at 0.5 or 0.4, what I'm going to do is I'm going to comment this out. You can use comments in MATLAB. They're just the % sign. You can see this is green now. And I'm going to pass in drag coefficient as an input. You can see I'm just going to span this block a little bit. We have our velocity and we have our drag coefficient. I can use the constant block to just set a constant input. In this case, if I do 0.5, that was the last drag coefficient of our simulation. This is the exact same behavior we just did. Instead of defining our drag coefficient in this compute drag function, I'm just doing it outside and passing it in. So when I run this, our apogee altitude shouldn't change. Let's double check. Yep, didn't change at all. The cool thing is this doesn't have to be constant. So what we're going to be doing is actively changing the drag coefficient with our guidance and control laws. There's going to be this intermediate step on our actual rocket where we'll have to turn a commanded drag coefficient into a commanded Airbrakes deflection angle. That's the thing we're actively controlling on the actual vehicle. But in terms of MATLAB, all we're going to do is our guidance and control laws will output a different drag coefficient. So here's my MATLAB model, including some guidance and control systems. You'll see this first block that I labeled physics is the exact same thing we just created. I've got my demux block and my rate limiter to get us our apogee altitude. I've got our position, velocity, acceleration, and you can see our drag calculation function is taking in our drag coefficient and our velocity, and we're outputting our drag force. I then have three different types of guidance and control laws here. So these first two guidance and control systems are something called reference trajectory controllers. So we're controlling based off of a reference trajectory. My assumption for my rocket is that my starting drag coefficient with my Airbrakes closed is 0.4. That comes from OpenRocket, and it's probably pretty accurate. My assumption is that my maximum drag coefficient is 0.7. I made that number up, and in our first flight test, we'll see how close I am to reality. That is a vibes-based engineering approach, which doesn't always work, but that's okay. In OpenRocket, I manually overrode my drag coefficient, and I set it to the middle between those. So in this case, that's 0.55. And I generated a trajectory that gets us to 240 meters in altitude with that drag coefficient. Now, I am basically taking that plot of velocity and position from OpenRocket, and we're going to use that as our reference. We want our rocket in simulation here to fly the OpenRocket trajectory to get us to exactly 240 meters. How we're going to do that is we will be comparing our rocket in simulation and hopefully in real life's position and velocity to the position and velocity of that reference trajectory. If we are higher than we should be based on our reference trajectory, we'll deploy our Airbrakes more. And if we're lower than we should be based on our reference trajectory, we'll pull our Airbrakes in. There's a couple different ways to do that. So the first one is something that I'm calling a velocity delta controller. With this guidance control law, the question we're asking is, at this given altitude, what is the velocity in my reference trajectory? We're going to compare our rocket's simulated velocity to that reference trajectory. So let's say our rocket is at 200 meters in the air. We should be going, let's say, 40 meters per second. If our rocket is actually going 38 meters per second, we need to close our Airbrakes a little bit. If our rocket's actually going 45 meters per second, we need to open our Airbrakes a little bit. How much we open them is our control gain, which you can see here. That's the tuning function that we'll have to change through simulation and through flight test. Specifically, what we're controlling here is apogee altitude. We don't necessarily care when we get to apogee, we only care about getting to apogee at the right altitude, no matter what time it is. In MATLAB, I've done some interesting things to get this controller working. So first, I'm pulling in our flight profile velocity and flight profile position. This MATLAB function block, find velocity error at altitude, does some interesting stuff. What this function is doing is it's looping through all of the positions in our flight profile position, and it's finding the first position that's above our rocket's current position in simulation. It's going to say, hey, that's pretty close to where we want to be looking at. What is the velocity at that flight profile position? Our delta V here is our vehicle velocity minus the flight profile velocity at position I, which is the position in our flight profile at our altitude. We're outputting our delta V and our velocity at I. Our output, delta V, we're going to multiply that by some control gain. I tuned this in simulation, and 0.6 seems to work for me. It's important to remember that this flight profile was generated with a drag coefficient of 0.55, so I'm adding that in as kind of our baseline. This kind of control system outputs 0 if you are on your flight profile. We can't command a 0 drag coefficient. We want a 0 change in our drag coefficient from our baseline. So it's important to set our baseline drag coefficient to be the same number that our flight profile was generated at. I'm then doing a little bit of servo dynamics. So this is the rate limiter block showing up again. I figured that we can change our drag coefficient by about 1.2 every second. This means us opening and closing our air brakes twice a second. I get this number from observing the behavior of the servo that I have, but this number might change depending on how your mechanism works and how fast your servos are. The next thing we're doing is we're limiting our output drag coefficient to our maximum and minimums that we have set. The minimum is 0.4 with our air brakes closed. We can't get any sleeker than that. And again, this maximum of 0.7 is something that I'm guesstimating, and through flight tests we'll see. This means that we can't command like a 90 drag coefficient and have our rocket stop instantly. We're then outputting our commanded drag coefficient, and through these switches I can select which controller we're going to use. We're plugging that drag coefficient into our drag calculation, and then we're doing the exact same physics that we talked about before. Now before we run our simulated control law, I've set our drag coefficient back to the constant 0.4, and let's see what altitude we get to. So this is showing we get to 264 meters. Again, we've commanded our rocket to go to 240, so this is a little bit high. Let's get rid of this constant, and let's plug back our drag coefficient input to the output of our velocity delta controller. We run the simulation again. Instead of 264 meters, we get to 247.9. So we're about 8 meters high, but we have certainly reduced the altitude our rocket flew to. Let's try something. Let's increase this control again. Let's try 0.8, and let's run this again. Instead of 247 meters, we should go a little bit lower. Oh, that didn't help. That's 248. This is what you can do for control gain tuning, is you can play with your control gains and see how your simulation behavior changes. So let's try a different control gain. Let's try dropping our control gain down a little bit. Instead of 0.8, let's try 0.4 and see if that changes our rocket's behavior. 247.7. So as you can see, changes to this control gain are changing our rocket's performance, but only slightly. One of the things that we can do is we can look at our velocity error over time. What you'll notice is that our motor thrust, it looks like our motor is not accelerating us as fast as our flight profile would suggest. And then as soon as we burn out, we're going a little bit faster. That makes sense because we want to be slowing down a little bit, so we want our air brakes out a little bit. But it's a little surprising that we're going fast. The fact that we're going fast and we end up high all the time makes total sense to me. The other thing that we can look at is our commanded drag coefficient. You can see that our rocket is basically slamming its air brakes all the way open until about 7.5 seconds, and then it's going back to 0.55. But this is happening a little bit after our motor burns out. So it looks like we're coasting for a little bit and then slamming our air brakes all the way open. So you can see this type of controller isn't working very good. Let's try a little bit of a different one. The next type of controller we're going to look at is a more typical PD controller. So that's proportional derivative controller. We're also referencing our flight profile here again, and I've used a little bit different block. This is the from spreadsheet block. These two different flight profile input constants are giving us the entire list of position and velocity data over our entire flight profile. And then every single frame we are looping through to figure out what position matches us the most and then looking at that velocity. The from spreadsheet function is referencing the time in our flight profile file, the Excel file. So this from spreadsheet block will give us the output altitude and velocity and the acceleration, though we're not pulling from it. in the flight profile spreadsheet at whatever time in the simulation it is. So 2 seconds into the simulation, it will give us the output altitude and velocity, one number each, at that specific time, 2 seconds into our flight profile. So we can't look ahead or behind us. This is only giving us one number every frame of our simulation. A proportional controller looks at our altitude. This line here goes all the way up, and you can see this is our altitude position, our Z position. And we're comparing that to the altitude in our flight profile at a given time. That generates an altitude error. This is also known as putting us in error space. And we're multiplying that by some control gain. That's the P portion of the PD control, the proportional. Our output drag coefficient here is proportional to the difference in altitude between our flight profile and our rocket's current position. The D is derivative. This isn't like a strict PD controller that you'd normally see. Typically, a PD controller would look at the rate of change of your altitude and try to drive that rate of change to 0. Specifically here, we're not trying to drive our velocity to 0. We're trying to drive the error between our rocket's vertical velocity in simulation and our vertical velocity in our flight profile to 0. So it's a little bit of a modification of the normal PD controller. So we're basically doing the same thing for velocity. We're taking our input velocity, we're subtracting the velocity at that given time from our flight profile, generating a velocity error. That's multiplied by our control gain, and then we are adding our altitude and our velocity control gain outputs with 0.55, which is our neutral. Again, this type of control law will output 0 if we are at the right altitude and velocity. The output we're looking for there is not 0 drag coefficient, it's whatever drag coefficient our flight profile was generated at. We then have some more servo dynamics. We're limiting our output to 0.7 and 0.4, just like we talked about. And then this servo dynamics block, again, is mimicking the fact that we can't slam our air brakes open and closed infinite times a second. That's generating an output drag coefficient. These cool little switch things let me switch the input to our drag calculation from one of these two different types of controllers. So you can see our velocity delta controller tried to get us to 240 meters, but got us to 247. Not very good. Let's now run our PD controller and see if we do better. 241.2. That's pretty good. Let's look at our commanded drag coefficient. You can see different commanded drag coefficient behavior from this type of controller from our velocity delta controller. You can see while the motor's still burning, we're slamming our air brakes open, and then we're a little gentle with them all the way around 0.55, and we're increasing towards the end. So it looks like we're still overshooting our altitude. As we get close to apogee, we're increasing the amount of air brakes command that we're outputting from our controller. The next thing I want to do here with this PD controller is do something called sensitivity analysis. This is where we play with our control gains a little bit and see if we can improve the behavior of our controller, try to get us right to 240 meters in altitude. So let's change this one. Let's increase our velocity delta, or our velocity control gain. So let's change that to 0.8 and we'll rerun it. Let's see if this helps our final output altitude. 240.1. Wow, that's really good. We're trying to get to 240 meters. We got to 240.1 meters. So it looks like setting our velocity gain a little bit higher made our rocket behave a lot better. What if we double our P gain? Let's try and make this 0.4. Let's see what happens to our rocket now. We get to 242.5. So it looks like increasing our proportional gain didn't help our rocket. So let's set that back down to 0.2. Now again, this is a simulation. Simulations are models. All models are wrong, but some models are useful. In this case, doing a lot of gain tuning in MATLAB might help, but at a certain point it won't be super helpful because the MATLAB simulation behaves differently than our rocket in real flight. Our goal with the simulation is not to build a perfect representation of the physics of the real world. Our goal is to build a simulation that's close enough and gets us control gains that get us in the ballpark. Flight testing will narrow those control gains down and get our rocket to behave perfectly every time. We have to rely on flight testing to do that very fine tuning because that fine tuning is below the threshold of the physics model in our simulation. So here's our PD controller. We can see the behavior of the PD controller and the velocity delta controller are a little bit different even though they're both looking at reference trajectories. One of the interesting things about the PD controller that we have here is that we're not just trying to control final apogee altitude. We're actually trying to get the rocket to fly the exact reference trajectory that we have. So we're trying to have the rocket fly at the exact right velocity all throughout the flight. We're trying to have our rocket fly to the correct altitude, and it's supposed to get to the correct altitude at the right time. If our goal with this rocket is to only get to the right altitude, don't care how long it takes, this controller is a little bit more sophisticated, or it's trying to control kind of the wrong things for us. So let's look at one more type of control law that's a little bit out of the scope of normal control theory, but might be more accurate than the other two. That's called predictive guidance. So in this case, we're not using kind of classical control theory with PD controllers and Bode plots. What we're going to do is every frame of the rocket's flight computer, we're going to run a number of live simulations to predict how high our rocket will go with different airbrakes deflection angles. We'll then pick whatever one's the best and put our airbrakes there. This is kind of like the brute force method of computing the correct airbrakes deflection angle. Again, we're literally simulating live at a specific point in time what our rocket's apogee will be if it continues to fly vertically with a number of different airbrakes deflection angles, and we're picking the best one. We can see we have a MATLAB function block here that's taking things like the current time, our target altitude, and our vehicle's position, velocity, and acceleration. Our outputs are the time to apogee, our apogee altitude, and our commanded drag coefficient. Let's see what's going on in this apogee predictor function. So here's our apogee predict function. We're taking in our position, velocity, and acceleration vectors, and then instead of doing the demux block, we're just taking their second vector elements inside of the code here. We're also taking in a constant target altitude. I guess you could change this over the course of the flight, but it's probably best to just leave it at a constant value. And then we're also taking in the current time. The current time is useful in predicting what our final apogee time will be. That's one of the mechanisms that we can use to debug this simulation. So let's take a look at the structure of our simulation. This for loop right here is running through a whole bunch of time steps. You can see our time step is defined here as 0.01 seconds. We're doing a simulation step 100 times a second. And this for loop is basically computing the force on our rocket as a function of our drag and then also of gravity. Our vehicle acceleration, F equals ma, we'll rearrange that. If acceleration is the force over our vehicle's mass, our velocity is our old velocity plus our acceleration times delta t, and then our altitude is our altitude plus our velocity times delta t. This is a Riemann sum integration. There are more complicated mechanisms of integration, of numerical integration, like trapezoidal Riemann sums, but we're going to stick with a normal, in this case I think it's a left-hand Riemann sum for now. And then we're checking to see if our vertical velocity is negative. That means we've reached our apogee and we can end our simulation and output whatever that altitude is. So this set of code will run a little simulation that's basically doing the same thing that this set of MATLAB blocks does. The idea, though, is that we'd code this apogee predictor into our actual flight controller. So this set of code just outputs for an input drag coefficient whatever our final apogee altitude will be. That's not actually super helpful. What we want to do is run that simulation a whole bunch of times with different drag coefficients and see which one's the best. That's what this outer for loop with the variable c is for. We're starting with our clean drag coefficient, and we're incrementing it by 0.02 with each implement of c. This gives us a range of 0.4 to 0.7 on our drag coefficient. As you can see, we're starting out with the smallest drag coefficient, which means our rocket should probably fly high. We're continuing to increase our drag coefficient with successive simulations until finally our apogee altitude is less than our apogee target. That means that our rocket is now just barely not quite making it to our target apogee altitude. At that point, we output that drag coefficient as our final drag coefficient. So you can see here again, this is an individual simulation running from the current rocket time to apogee, and we're doing that a whole bunch, at least 15 times, and then we're taking whatever drag coefficient gets us to just below the right apogee, and then we're outputting that. We then pass that into the same servo dynamics block, and that is going into the command for our drag calculation. If we run this, we expect to be just a teeny tiny bit short of our target apogee, and we are. We're trying to get to 240 meters, and we got to 239.5 meters. Now, these types of predictive guidance are super powerful. You can model all sorts of interesting behaviors that you wouldn't expect to be able to model with classical control theory. We're using predictive guidance here for an Airbrakes rocket, but you can do predictive guidance for all sorts of other aerospace vehicles. Instead of relying on a closed-form mathematical model, you're just running a bunch of simulations and seeing which one's the best. There are all sorts of ways to improve this apogee predictor. Instead of just picking the final drag coefficient that gets us a little shy of our target altitude, what we could do is linearly interpolate between the last two simulations that we ran to try to get to exactly 240 meters. That's one change that I'll probably make here in the near future. One thing you'll notice is that this type of predictive guidance doesn't have a control gain that we're going to change. Basically, this apogee predictor is just outputting a drag coefficient, and that's the one that we're using. We're not looking at altitude errors or anything like that. There still are tunable parameters, though. One of the tunable parameters is the time step of our simulation. In this case, each of the internal simulations, we're running these every single frame on our flight computer, the delta time of those simulations is 0.01 seconds. So in simulation, we're computing the drag force and the gravity force on our rocket 100 times a second. Let's see what happens if we decrease this to 0.1. So now we're only computing that 10 times a second. We'll run this and we'll see what happens to our apogee altitude. So now we're ending up 2 meters high. Let's see what happens if we change that even further. This is pretty dramatic. Now our delta T is going to be 1 second. In simulation, we're predicting our rocket position, velocity, and acceleration every second. One time every second. That's probably not a very good physics model, is it? And as you can see, we're way high. This is part of sensitivity analysis. What we're doing is we're seeing how sensitive our rocket's final behavior is to changes in our simulation time step inside of our apogee predictor. So let's set this back to 0.01 because that one works pretty good, 0.01. The other simulation parameter we have is how many different drag coefficients we're looking at. Let's do something dramatic. Let's do 2, and we'll increment this by 0.1. Actually, we'll go up to 3. So this means instead of checking 15 different drag coefficients and seeing which one's the best, we're only going to check 3 different drag coefficients. Let's see if that materially changes the behavior of our rocket. Wow, what you can see is we're still getting to 239.8 meters instead of 240. So it looks like our apogee predictor isn't very sensitive to how many different drag coefficients we check. This type of sensitivity analysis is super important. It lets you know what you need to focus on. It looks like we need to focus very heavily on running our simulations in our apogee predictor with a short time step, but it looks like we don't need to check very many different drag coefficients. That's going to let us optimize the software on our flight computer and let our flight computer run even faster. So let's just recap what we've done today. First, we built a physics simulation of a rocket flying vertically, and we outputted its apogee altitude to this cool little display. We then checked 3 different types of guidance. The first version of guidance and control I called the velocity delta controller. Our output drag coefficient is only a function of the difference in velocity between our reference trajectory at our current altitude and our current velocity at our current altitude. This is trying to get our rockets to the correct apogee, but it's only looking at our velocity to make the decision of how much our air brakes need to deploy. The second type of controller was the PD controller, and this is a little bit of a different PD controller to the ones you normally see because we're comparing our rocket's current position and velocity to the position and velocity at the current time step in our reference trajectory. This one definitely performed better than the velocity delta controller, but it required a little bit more math. We also have more tuning parameters to change, so it's a little bit harder to get the right combination of velocity and position control gains. Both of these controllers, though, suffer from the same problem that we're reliant on having a good reference trajectory to start with. If we have errors in our reference trajectory, like our parachute deploying inside of our reference trajectory, or maybe the reference trajectory's drag model's not very good, then the output of our controllers won't be very good either. We're reliant on having a good reference to compare against. We also looked at a predictive guidance controller. We're not really doing classical control theory here. What we're doing is every single frame, we are predicting a whole bunch of rocket flights all the way to apogee with different drag coefficients and just picking the one that's the best. This is obviously way more computationally intensive, but this type of controller performed the best, at least in simulation. What we're going to do when we've completed our Airbrakes rocket is I'm going to code all 3 of these into its flight controller, and we're going to try all of them in flight. And we're going to see which one performs the best, not just in simulation, but in real life. So I hope you all found this video really interesting. If you're just getting into simulation, I would highly recommend checking out MATLAB. They have great simulation tools, they have great programming tools, they have great data analysis tools. If you're a hobbyist, you can actually get MATLAB with a permanent license. The pricing is super affordable for just a hobbyist like myself. And if you're at an institution, you're at a university, or you're at a high school, your school might have MATLAB licenses available for you. If you're interested in seeing how I use MATLAB for more complicated full rocket guidance and control simulations, check out this video that I did about a year ago explaining my simulation process going from initial rocket design through guidance and control simulation all the way through to software in the loop testing. I'm working really hard building my Airbrakes rocket and Sapphire, my supersonic actively controlled amateur rocket. So if you're interested in seeing either of these projects and more, make sure you're subscribed, and I'll see you all in the next video.